Thanks, Vincent, for the nice introduction, and also to Simon. So you guys both for inviting me in this nice PhD postdoc series. So yeah, as mentioned today, I will bring again the topic of organic solar cells, and in particular, I want to highlight this very interesting material, tin oxide. Maybe some of you will be familiar with, especially from the field of perovskites. And I want to show what we've learned about how to use it in our solar cell stacks. But also simultaneously, I will try to describe how important it is to study the surface chemistry of all our layers when doing a solar cell. So let's start by looking at one of the most commonly shown plots in our field. So we have the power conversion efficiency over time of perovskite organic and emerging PV fields. Um, it's crazy to see that actually in just the time span of my PhD already 3 or 4% of our power conversion efficiencies it increased in the field of organics. And this is also together with perovskites, of course, really interesting to bring the field towards technological transfer quicker. And what is the reason for this increase? We all know that, and we can actually dissectionate a little bit where it's coming from. So in a solar cell, we have a photoactive layer that we are continuously improving. So the field is, especially in organics, is studying into a lot to make better molecules, so we can improve the performance of our solar cells. But it's intriguing to see that even with all these years of progress, the both electron and hole transport layers, so these layers that we grow in our devices to gain selectivity in our charge carrier extraction. So as I was saying, these transport layers have been kept more or less the same. So there are very few options that can lead to a good device performance. And that's the inspiration for such a project. So in my case, and actually for this presentation, I want to focus on the electron transport layer. And in particular, I want to focus on tin oxide. So for the ones who worked with tin oxide already, it's large bandgap allows for high optical transmittance. It provides with high electron mobility and hole blocking capability, which is great to work as an electron transport layer. But also compared to other benchmark materials like zinc oxide, it provides lower reactivity, and it can also be deposited through a low temperature deposition process. So having this as a starting point, we decided to explore this material as our electron transport layer. And I'm showing here my system components. So again, tin oxide we will use to deposit from a solution of water-based colloidal nanoparticles. It's actually a rather well-known formulation, usually referred as alpha tin oxide. And of course, it's really interesting because it can be easily scalable to an industrial process. Now, I'm showing also here my two blends that I used in our project. So they are a combination of polymer donor and small molecule acceptor, as a big part of the community is working with, and they have already been reported to yield rather good performances. So let's have a look now what happens when we build a solar cell with these blends and we use tin oxide as our electron transport layer. So very simple slide. I'm showing here a JV for the blend 1 and a JV for blend 2. And we can extract the power conversion efficiency around 11% and 15% for the other blend. Now, I'm not showing everything here. So if I'm actually fully honest, in order to get this efficiency and this good shape, the diode shape of the solar cell that we are expecting, it actually required of around 15 minutes of illumination time, so that this S-shaped JV can be fully, let's say, in an ideal JV curve. This is some kind of phenomena that's called light soaking phenomena that's been already reported in the literature. And it's ascribed to the non-ideal interface between one of your transport layers and the active layer. Now, of course, we want to avoid this problem, and we are even thinking this might be one of the reasons why tin oxide is yet not a benchmark material in OPV. So we went a little bit in the literature to explore what other people did with tin oxide, and we were surprised to see that most of the reports on tin oxide are actually on passivation. So everyone that has worked with tin oxide, mostly in the field of OPV, but also quite a lot in perovskite, they are claiming they have this consensus that tin oxide and in particular this alpha tin oxide requires a surface passivation. There are some examples using physical treatments like UV ozone or oxygen plasma, but even some molecular modification on the surface. In some cases, even a rather complicated type of passivations. So when we explored this literature, we actually came up with the idea that many things could passivate tin oxide, but there was not a real real description of what are the defects or what are the source of this non-ideal interface with the organic layer. And that's the reason why we proposed ourselves this solution. So I will call solution 1 to study the surface properties of our tin oxide nanoparticles. So starting from here, we studied the thin films of our tin oxide, and we characterize them with Kelvin-proof force microscopy so that we can understand if the Fermi level is well aligned with our small molecules. This is the case. So we extracted the value, and we see that in principle there shouldn't be an extraction barrier from the electron extraction point of view. And then we decided to characterize the nanoparticles from solution. So we did some DLS and some electrokinetic potential of study of the nanoparticles. So we see a little bit, okay, what's we have a rather narrow distribution of the sizes, around 13 nanometers of size. And we saw that it has a high negative electrokinetic potential of minus 34 millivolt. Now, this is an indication that we have presence of positive counterions in our solution. And this actually agrees with the fact that we are encountering a high pH. Now, let's remind ourselves that this solution was in water, so we need a strong ligand to make the nanoparticle stable in water. In reality, not even from these measurements, but also we saw that after precipitating and rewashing these nanoparticles and redissolving them in water, we could still get a stable solution while choosing a slightly different polarity solvent like methanol, they became unstable, meaning that these surface ligands of the nanoparticles are really solvent sensitive and probably very strongly bonded to our nanoparticles. So we hypothesized that these ligands might still be present in our films. So that's the reason why we went to study a bit deeper the surface chemistry, and we did some X-ray photoelectron spectroscopy. I'm showing here on the left the wide scan measurement, and here we can I'm just displaying the relative atomic concentration of each of the atoms present on the surface. So tin and oxygen, they are obviously there. We observed as well a decent amount of carbon present on the surface, and we were surprised to see that also potassium. So these are the 2p orbitals from the potassium atom have a large presence on the surface, in this case close to 10%. So we thought, okay, maybe these potassium cations are coming from those ligands that need to be necessarily there to make the solution stable. And those could be the cause of our inefficient electron extraction. So let's go back to do some films. This is the usual process we do for our tin oxide deposition. So deposition, thermal annealing at 150 degrees. And we decided to do something very simple. So since we have potassium, supposedly potassium cations on the surface, let's try to just wash it away with some deionized water. And then we followed by another drying step at 100 degrees in air to remove this water. And then let's see what happens. So this is what we did. And these are the XPS again of the thin films of tin oxide before and after the DI washing is performed. So as you can see, tin, oxygen, and carbon remain equal without not even a little shift in the binding energy, but we can see that the potassium cation is fully removed. So we are going from this 10% I was showing before to 0%. We did some FTIR, so I'm displaying it here at the left. So this is infrared spectroscopy, and is essentially a technique that can help us to identify functional groups on the surface of or in liquid state or in solid state. So I'm showing here the core for pristine and the DI washed tin oxide. And we can see that in this region, that's typical for the carboxylate frequency mode. We are going from something that contains both carboxylate and carboxylic acid to a fully carboxylic acid situation. So what we are proving is that our surface washing is just removing the cations and is leaving our surface in the carboxylic acid mode. So that's interesting, but let's go a bit into the solar cells. So this is what I was showing at the beginning. My pristine tin oxide, we have some light soaking, and this is the solar cell characteristics. And when we perform the DI wash, for both blend 1 and blend 2, the first thing that we observed is that there's not light soaking anymore. So we got rid of this waiting time that I was mentioning before. And simultaneously, we observe an increase in the short circuit current. So we are going in both systems to around 1 milliamp or even more of short circuit current. And this is, of course, really interesting for the power conversion efficiency that goes up to almost 13 and 16.3 for blend 2. So let's try to understand a bit more what's going on here. We did some impedance spectroscopy in order to address the mechanism behind. And what we observe is that we have actually an increase of the time constant of the system. So what I'm displaying here is the real part and the imaginary part of the impedance. And from here, we can extract an equivalent circuit. We can extract parameters of the system. So this RC is directly correlated to the lifetime of the injected carriers, in this case, of the system. And we can see that in the DI washed, so this one in purple, these carriers live longer. This makes sense because we are reducing in surface recombination. Something else that we are observing is this secondary peak, secondary relaxation time at a very elevated time constant. And this, again, we ascribe to the fact that these electrons have a barrier for extraction, and therefore they become slower at the interface. So, in brief, we have a system in which initially our surface of our interface with the organic layer contains these potassium cations that are electrostatically bonded with a ligand. They create Fermi level pinning with our LUMO level of our organic layer. And this is presenting a barrier for extraction due to the accumulation of electrons. What we are doing with the washing, we are essentially reducing this barrier for extraction, and we are maximizing the electrons that can be transported in the bulk of the tin oxide. So till here, everything made sense. Okay, sorry. Let's also have a look at the stability. So what I'm presenting here is the operational stability of blend 1 and blend 2 in an MPP track. So meaning we are continuously measuring the solar cell at its maximum power point and under one sun condition. And what we observe is that our washed tin oxide in both systems improve dramatically the operational stability. And again, the parameter that is mostly affected is the short-circuit current. This is, of course, really interesting because what we are saying is that by something purely coming from the material, thanks to the fact that we studied the surface chemistry, and without any extra passivation, we improved dramatically the stability of the solar cells. So it's not only this 1 or 2% of efficiency, but we can also go ahead and check and see that the stability is also improved. So what else did we do? So we wanted to convince ourselves that it was something so simple as these potassium cations on the surface. So what we did is to develop this reverse experiment to bring back the potassium cations on the surface. So after we made our process of washing away the cations, we decided to use potassium hydroxide to retreat the surface and to bring back these potassium cations, and again doing an equivalent drying. We choose these two concentrations, and the results are here. So the light soaking is back again there. So we see that also with the higher concentration of potassium hydroxide, this is even more pronounced. And what I'm showing in the right side is the power conversion efficiency over time. So again, the photostability is compromised. So we have here the DI washed and the pristine, and then with these treatments, the stability is even more compromised. So this is again an empirical proof of our hypothesis, and we are really happy that we observed that just by washing these potassium cations, we could improve both efficiency and stability. So I just wanted to show very briefly where we were compared to the literature, because this is something that you need to do, not to show off, but actually to understand if what you are doing makes sense with the systems that other people are using. So in this case, I'm reporting here all points from literature using tin oxide. And so we would be also in black, so nanoparticles, and we are essentially very high in PC and fill factor. But we were actually considering that there could be some room for improvement. And that's the reason why we thought of avoiding these solution processed problems, if you want to call it like that, and go to an alternative deposition method. And this alternative deposition method is atomic layer deposition. So for the ones who are not familiar with atomic layer deposition, it is well, there's this schematic here on the right side. So we have a chamber that we use at high vacuum, and we let some precursors or reactants to react on the surface in a self-limiting manner. And that's why we have an like inlet and purge step that goes in loops, and let's say we are building a layer by layer film. What is the interesting things about ALD? Well, it allows for deposition of compact layers. So this is highly used, especially for oxides, also in other fields. It allows for very good thickness control. We can tune the temperature of the system and therefore the optoelectronic properties. And finally, it's also, even if it's not intuitive, it's also scalable and industrially used. And for this point, I wanted just to give this little example that I found around, that there are companies already selling ALD machines that can be combined with roll-to-roll processing. So what we did in this case is to grow tin oxide. So we are using tin precursor and water, and we selected 3 different temperatures to study the materials properties at each of them. So I'm briefly showing here again the KPFM measurements we employed, so we can tune the Fermi level at the surface of each of these ALD tin oxides. And what I'm showing here in the bottom is that the AFM images of these layers, and is that this nanocrystalline structure that we are growing actually changes as well with temperature. So we are seeing some different crystalline grain size at higher temperatures, while we have something more, let's say, close to what we expect from our ITO substrate at lower temperatures. So what we did next was to build some more layers, to grow some more layers to characterize the optical and electrical properties of this material. So I'm showing here the optical band gap from the tag plot, the 3 different temperatures, the transparency. And what we can quickly observe is that as we decrease temperature of our ALD tin oxide growth, we are improving the transparency of the layer. So this is, again, an important feature if we are building an electron transport layer. And we also characterize the current density, so essentially the conductivity of our layers. And we see that there's also a trend with the temperature. So the higher the temperature, the higher conductivity. And this also correlates well with what we were saying before, related to the nanocrystallinity or the domain size of our layers. So let's look at the devices finally. So we have, I'm plotting here the 4 parameters of the solar cell with a lot of statistics. And what our main conclusions was that fill factor and the current are parameters that are mostly affected by our deposition temperature. And in particular, 140 seems to be the one which leads to the higher efficiency. In this case, let me plot it again with the graph that I was showing before. So we got a strong enhancement in fill factor. So the high compactness and quality of this ALD tin oxide allows for this growth, and with an interesting power conversion efficiency over 17%. We even compare this with again with the nanoparticles, the tin oxide by nanoparticles, and with what seems to be the benchmark metal oxide used in organic solar cells, that is the zinc oxide. So our self-calibration experiment led to the conclusion that the ALD tin oxide is actually the best performing system. And we can see also here from the EQE curves that the best system so far will be the ALD tin oxide. So to conclude my talk, so I want to claim again how important it is to study the surface chemistry of all our layers. This, of course, not only apply to OPV, but also to any device stack type of experiment. And in particular, people working in perovskites might suffer from this kind of issues. So we were the first ones to report what is the main problem that alpha tin oxide is causing in OPV. And we show an easy solution to improve both the efficiency and the stability. So yeah, this is essentially what I'm saying here. And finally, the tin oxide, we show that it can also be grown by atomic layer deposition. We are still using it. We are very happy with the quality that we can get. And in particular, our power conversion efficiencies that we get in the lab are really outstanding in our opinion. So with this, I would like to thank my group in University of Groningen, photophysics and optoelectronics. In particular, Professor Maria Loy, my supervisor, and everyone who collaborated in these projects, the funding agencies, and also, yeah, here for your information, there's also the references of what I presented. And thank you all for your attention.